Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is the final video in derivatives of trigonometric functions for Calculus 1. And in this video, we're going to just explore some higher level questions that involve synthesis of a bunch of older skills. So let's go ahead and start here with just a nice function, which is a mixture of an algebraic function and a transcendental function. Consider this function, f of x, which is equal to 1/2 x, that's the algebraic part, plus cosine of x, that's the transcendental part, on the interval from 0 to 2 pi. Graph this function using Desmos and discuss how you would find the local extrema of this function on this interval. So let's go ahead and do that. And here's the function from x equals 0 to x equals 2 pi. It's all the way over there. And if you don't recall from your pre-calculus course, local extrema are the maximums and the minimums on this interval, not including the edges. So you can't include the edge points, but you sure can talk about, like, for example, this looks like a local maximum because that's where the function becomes the highest point locally. And then down here is a local minimum. Now, how the heck could you find those points? And this is something that my pre-calculus students are currently struggling with when we talk about, okay, well, we're going to graph this function, and they start saying, well, how do I know what those highs and lows are? And my response is, you won't until calculus. So how could we use all the information that we've had up to this point to get a value for the x, or find the x values for where these minimums and maximums occur? And if you click on this, by the way, it'll automatically tell you it's 5 pi over 6 and pi over 6. But let's not adhere to that. Let's just pretend that we're not allowed any type of technology. How would you, without technology, find those values? Well, think about it this way. Along this interval right here, the slopes of the tangent lines are positive. And along this interval over here, the slopes of the tangent lines are negative because it's decreasing. But at the minimum right here, the tangent line should have a slope of 0. And at the maximum, the tangent line should also have a slope of 0. Now, I don't want to lead you astray and tell you that all maximums and minimums occur when you have a slope of 0 for your tangent line, but that's a good starting point. So we really, in this case specifically, want to find out when f prime is equal to 0, because our slopes of our tangent lines would be 0 at that point. Now, I do want to tell you that maybe I should copy that function. That function kind of looked like this. So slope of the tangent line is 0 right here. Slope of the tangent line is 0 right there. Now, if our function looked like this, then you cannot say, I want the slope to be 0 to find that minimum point. That's just not going to happen. You cannot find that x value for the minimum there by using a slope, because the slope doesn't exist there, or the derivative does not exist there. So that's just a heads up. It's not always going to be the case that you would set f prime to equal 0. However, for nice smooth curves, that is the case. Now, I didn't ask you to do it in this problem, but why not? Let's just find out the x values when the slopes are 0. So let's go ahead and take the derivative here, f prime of x. The derivative of 1/2 x is just 1/2. The derivative of the cosine is a negative sine. And we want to solve 0 is equal to 1/2 minus sine of x. Or in other words, sine of x is equal to 1/2. The reference angle is pi over 6, and sine is positive in quadrants 1 and 2. So therefore, our solutions are going to be pi over 6, that's quadrant 1 solution, and 5 pi over 6. That's a quadrant 2 solution. And remember, we only want the solutions between 0 and 2 pi, so that's perfect. And that matches what we saw in the Desmos graph. That's a good way to do it, just setting the derivative equal to 0. It won't always work, again, if you have a function that has any type of cusp or corner, or technically discontinuity. Now, let's say you're going through the homework, your professor assigned a bunch of problems, and you run into this guy right here. And let's pretend you've never had calculus before, because that's a critical assumption for this problem. So therefore, you do not know something called the chain rule. And somebody says, I need you to take the derivative, the second derivative, of this function, which is secant squared. You can't, nobody told you what the derivative of secant squared was, right? So you have no clue what the derivative of secant squared is, but you know what the derivative of secant is. And so you should write this as needing the second derivative with respect to x of the secant times the secant. That's the secant squared, secant times secant. And now you can use a product rule. So let's go ahead and take the first derivative. The first derivative of secant times secant. Again, if you happen to have had calculus in the past, do not use the chain rule for something like this. Instead, I mean, you can once you have the chain rule at your disposal, but until your instructor has introduced it, assume you cannot use it. And so in this case, we'll just take the derivative of this product. So the derivative of the first thing, which is the secant, is going to be the secant tangent times the derivative of the second, or times the second object. And in fact, you know what I might do? I might color code these. So let me color code these so that's a little bit easier. Derivative of the black is secant tangent times the green plus the black, which is secant, times the derivative of the green, which is secant tangent. Now, I know this is an absolute mess. It's secant squared times tangent, and you have two of them. So this compresses down to be 2 secant squared of x tangent of x. And I totally get it if somebody says, oh, are you kidding me? Because we're going to take another derivative. We've only taken the first derivative, and we need one more. So let's just do it. All right. So the derivative, I should say, maybe I should write this in blue. I'll keep it in blue, actually. The derivative, second derivative that is, with respect to x of secant squared is going to be the derivative with respect to x of what we just got. It's the derivative of the derivative. Now, you don't have to be so exhausted here when I'm about to do this. First of all, note you can factor out the constant. 2 times the derivative with respect to x of the secant squared times the tangent of x. Second thing you should note, when we take this derivative, we're going to use the product rule. You don't have to write this as the secant times the secant times the tangent, because I already know what the derivative of the secant squared is. The derivative of the secant squared, let me write it here, derivative with respect to x of the secant squared is 2 secant squared tangent. So when I do this product rule, and I should have color coded it, I apologize. So let me write it, secant squared of x, and this will be the tan of x. All right, there we go. Using the product rule, so 2 times the derivative of secant squared, so the derivative of the black function there. Well, we just found out the derivative of secant squared is 2 secant squared tangent of x. 2 secant squared tangent of x times the green function plus the first function in black times the derivative of the green function, which would be a secant squared. So notice I'm using a result, the derivative of secant squared, within this. It's just much easier to do that. You can see this is going to be 2 secant squared tangent squared plus secant to the 4th, but I can always factor out a secant squared. Why not, right? And when you do that, you're left with 2 tan squared plus secant squared of x. And this is very enticing to want to manipulate this, but this will not reduce down very much. I mean, you could use the trig identity that secant squared is 1 plus tan squared. You could totally use that if you wanted to. If you did that, it wouldn't really clean things up. It would just rewrite them, right? So you would end up with 2 tan squared plus another tan squared. You have a 3 tan squared plus 1. I don't think that's any better. So I probably wouldn't have done that, but you could opt to do that. So either of these answers are perfectly fine. That's a really good problem. Just showcasing for those who already know calculus that you don't always have to reach for the chain rule. And for those who have not taken calculus and don't know what I'm talking about, well then, earmuffs. We now arrive at one of my favorite problems to give, whether it's a homework or exam. I love pattern recognition problems, and this is ideal for pattern recognition. When somebody says find the 310th derivative of something, you know there's got to be a pattern. So how do you find the pattern? You start taking derivatives. So let's just start taking some derivatives. F prime of x, so the first derivative. Okay. That's going to be derivative of x times the cosine plus x times the derivative of the cosine, but the derivative of the cosine is a negative sign. Not much else I could do there. So let's go ahead and take the second derivative. Second derivative of f. Derivative of the cosine is a negative sign. Minus, I'll put this in a block here. Derivative of x is 1 times the sine, plus x times the derivative of the sine is the cosine. Now I can combine like terms, actually. I'd have a negative sign minus another sign, so negative 2 of those signs, and then minus x cosine of x. Now, early on, it's very hard to see a pattern. You can see they both involve cosines and sines, but that's probably about it. So let's take another derivative, a third derivative. And generally, a little hint for you, whenever you have sines or cosines, usually a pattern starts every 4. Because if you think about the first derivative, let's just say the sine. First derivative of the sine is the cosine. Derivative of the cosine is a negative sign. The derivative of a negative sign is a negative cosine. And derivative of a negative cosine loops you back to the sine. So I'm just letting you know that generally speaking, trig functions, at least sine and cosine, have patterns of 4. All right, third derivative, which is the derivative of this guy right here. Well, derivative of negative 2 sine is a negative 2 cosine. So let me write that in there. Negative 2 cosine of x. Minus, start a bracket. Derivative of x is 1 times the cosine of x. Plus x times the derivative of the cosine, which is a negative sign. Notice how I'm very meticulous with my grouping symbols, my brackets. Otherwise, I'll make a mistake. Distribute the negative through. You have negative 2 cosine minus another cosine, so you have negative 3 of those cosines. And then plus x sine of x. Now I start seeing a pattern emerge. Notice the coefficient here was a 1. And then it became, well, unfortunately, a negative 2. And then a negative 3. Well, I see the 1, 2, and 3 at least. That's part of the pattern that's happening. Also, I see another pattern. Each of these has an x, and an x. And each of them alternates sine of x, cosine of x, and a sine, again, of x. Okay. So let's see what the fourth derivative will do. We're going to guarantee it'll be 4 times something, and there'll be an x cosine of x. But let's just see what the pattern is here. So the fourth derivative of our function is going to be, well, let's see. Derivative of negative 3 cosine is a positive 3 sine. Plus, I don't need brackets for this. Derivative of x is 1 times the sine, and then plus x times the derivative of the sine, which is the cosine. Combining like terms, we have 4 of those sines, and then plus x cosine, which is exactly what we thought it would be. All right. And you see it's 1, negative 2, negative 3, and positive 4. That's weird. And it's a negative x sine, a negative x cos, positive x sine, positive x cos. So what's the pattern? Well, one final derivative will show it. The fifth derivative. Derivative of 4 sine brings us to 4 cosine. And then plus derivative of x is 1 times the cosine. And then plus x times the derivative of the cosine, which is a negative sine. Collect like terms, and you will see you have that positive 5 which we knew we would get, cosine, and then a minus x sine. Now, I want to highlight something that's important. Our first derivative ended with a minus x sine. Our fifth derivative repeats that. Our first derivative had a cosine there. Our fifth repeats it. So basically, every time that you get through 4 derivatives, showcase that, 1, 2, 3, 4, the pattern starts to repeat. Great. So I know every 4th derivative, the pattern will start to, basically once it loops to the 5th derivative, the pattern will repeat. So how many groups of 4 are in 310? Well, that actually doesn't matter. What matters is after you've gone through so many groups of 4, what's the remainder? Well, 300 is divisible by 4. So really all we have to worry about is how many times does 4 go into 10? Or not even how many times, but what's the remainder? Well, 4 goes into 10 twice, but with a remainder of 2. So this will land us first, second, third, fourth derivative, 5th, 6th, 7th, 8th, 9th, 10th, 11th, 12th, right? And all the way ... until you get to 300th, 304th, 308th, 9th, 310th. That's the pattern that I'm looking for. So again, that's why I was saying, what's the remainder after you divide 310 by 4? Because that will tell you which derivative to model after. I'm going to model after this derivative right here. It won't be a negative 2 sine of x minus x cosine of x. It'll be a negative 310 sine of x. So let me write that down. The 310th derivative with respect of x is going to be a negative 310 sine of x minus x cosine of x. Again, because basically the pattern repeats every 4, just the coefficients kind of keep with the derivative. You could see why this is true, by the way, if I would have made a simpler question and asked what is, for example, the 7th derivative. Well, if we got to first, second, third, fourth derivative, and notice the 5th derivative has the same form as the first derivative, then I could have said, oh, okay, well then the format for the 5th derivative is actually this one right here, 6th and 7th. Oh, great. Okay. And then I would have said that our 7th derivative would be a negative 7 cosine of x plus x sine of x. And I could have easily just said, well, you know what would have been easier is how many times does 4 go into 7 and what's the remainder? Actually, not even how many times does 4 go into 7. It's just what is the remainder after 4 goes into 7? It's 3. And that's how I know where to land. The really cool pattern recognition. I highly recommend spending some time on this and convincing yourself. The same pattern recognition is what you learned when you dealt with powers of I. Powers of I have the same 4 cycling, right? Here's a 5th power, 6th power, and so on and so forth. These are actually equivalent. 7th power is equivalent to that, and 8th power is equivalent to that. So, really cool stuff. I dig that style of problem. And last but not least is another differential equation style problem. If you don't know this, then you should go back to one of my lecture videos. I think it's in the polynomial material. Yeah, I'm almost positive it is. It's in the synthesis questions for derivatives of polynomials and exponential functions, where I describe what a differential equation is and how to get your supposed functional solution to work with that differential equation. And we're just going to go ahead and repeat that process here. So we are handed this and we're asked, find the values of a and b so that when you plug it into this differential equation, it becomes true. And the way that I told you to do this in the previous video was to find out what y double prime and y prime are. And in fact, I did it this way. I started with negative 2 times y because that's what I have right here. So what I'm going to do is find out what negative 2 times this y is. Well, that's kind of easy, right? It's just negative 2a sine of x and a minus 2b cosine of x. I'm also interested in y prime. Eventually, I'm going to add all these up. Y prime here, I'll just look at the y they handed me. This guy right here. Its derivative is a cosine of x minus b sine of x, because the derivative of cosine is a negative sign. And I also need a y double prime. I'm going to add all these up. Y double prime just takes y prime and takes another derivative. The derivative of a times cosine is a negative a sine minus, and then the derivative of b times the sine is b times the cosine. Now I will just add all those up and I will get the following. And before I do it, I should note, the way I'm going to add this up is I'm going to collect like terms of functions. So in other words, I'm collecting all the sines together, and then I'm going to collect all the cosines together. So that's what you're about to see, is that I have some sine of x with a coefficient of negative 2a minus b minus a. That's the coefficient of my sine of x. And then plus, I have some coefficient on cosine of x. Well, that coefficient of cosine of x is a negative 2b, a positive a, and a negative b. And in the end, when you have taken, because this is just y double prime plus y prime minus 2y, when you've taken all that stuff and added it up, they're asking us, please make sure that that is equal to 1 times sine of x plus 0 times cosine of x. That is, I want this to equal 1 sine plus 0 cosine. And then we do comparison of coefficients. The coefficients on, or the coefficient on sine over here is a negative 3a minus b. The coefficient on sine over here is a 1. The coefficient of cosine right here is a negative, actually I'll write it this way, a minus 3b, and the coefficient of cosine on the right hand side there is 0. Notice that's a system of equations with two unknowns. Two equations, two unknowns, I could totally solve that. I'm going to go ahead and multiply the second row by 3. I'm going to solve by elimination here. Multiplying that by 3. Oops, I get 3a minus 9b is equal to 0. 3, yep. And I'm going to add those two equations up, and I get that negative 10b is equal to 1. Let me write that down. Negative 10b is equal to 1, or b is equal to 1/10, negative. Now that I have what b is, I could plug it into either equation. Doesn't really matter. I think I'll go ahead and plug it into the top equation. Negative 3a plus 1/10 is equal to 1. That is negative 3a is equal to 9/10. That is a is equal to a negative 3 over 10. Is that right? I think so. Yeah, that is right. And so therefore, we found the a and b for that function, so that if we take its second derivative and add it to its first derivative and subtract from that twice the original function, it should turn into the sine of x. That is the solution to that differential equation. Y is equal to negative 3/10 sine of x minus 1/10 cosine of x. All right, and that's it for the synthesis questions. We are done with trigonometric functions.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at ease. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.